In this activity, we're going to turn things around just a little bit. I want you to start with a root locus, and I want you to backtrack your way to get the transfer function, the corresponding transfer function. And then I want you to use some of the logic that we have between making angles from all of these poles to a point on the imaginary axis that then slides along in order to sketch a vague sketch of what the Bode plot should look like. And then we'll take a look at the Nyquist plot and evaluate stability using our Nyquist criteria. So go ahead and give this a shot. Our first task in this activity is to start with the root locus and build out our transfer function. And so what we observe is that we have poles at -1 at plus or minus 2i. The plus or minus 2i, those each have a single branch coming out of it. And so each of those is, there's just one pole at each of those positions. They're complex conjugate. And together they give us this term of the transfer function. At the point s is equal to -1, there's two branches emerging from that pole location, and so that means that there's actually two poles located there, and so that gives us both of these terms that are located at -1. So that is our transfer function. We don't have any other zeros or any other poles, and so that characterizes the transfer function. And so now what we'd like to do is use the root locus to sketch out the Bode diagrams. So in this case, I've actually plotted the Bode diagrams, but let's capture a couple of the points that are possible through just kind of the geometric analysis as we've been doing using the root locus. So keep in mind that if we evaluate the transfer function at along the imaginary axis, so in this case it's the Bode diagram, so it'll be along the positive imaginary axis, that each of these terms can be thought of as contributing 1 over their magnitudes, which all those magnitudes multiply, and each of the phases enter in with a minus sign because they start in the denominator here, and all of those add together to create the overall phase. And so we have 4 poles, and so for the positive imaginary axis, so we're on the positive end of the imaginary axis, that means this phi 3 is always going to be at positive 90 degrees. So it will always be looking directly up to any point that could be here. So for this point that's right here, it's always positive 90. This phi 4, initially, when s is down close to the origin, below this pole at 2, then this phi 4 will be minus 90. And then once we cross it, that phi 4 will then be plus 90. And so we know that relationship is either going to be minus 90 or plus 90. And then this phi 1 and phi 2 that come from these two poles at -1, these are going to start at 0, and they're going to slowly increase. So when s is very close to the origin, so omega is very small, then that means that phi 1 and phi 2 are very small, so they're essentially 0. Phi 3 is plus 90 and phi 4 is minus 90. And so for that reason, the Bode diagram should start at 0 degrees. So asymptotically approaching 0 degrees as we hit smaller and smaller frequencies. So that's one thing that we can tell. The other thing we could tell is the fact that the magnitude at this point is going to be at that same point when s is very, very small. The magnitude from these s is equal to -1 points will be magnitude of 1. So m1 and m2 will be magnitude 1. m3 will be a magnitude of 2. And m4 is also a magnitude of 2. So that makes for 1 over 1 times 1 times 2 times 2. So that's 1 over 4. So the magnitude, the gain, should be 1/4. And that means that it will then you take the log of that in order to put it on the decibel plot. So we can see that actually down here in the Nyquist plot, if we want to go ahead and jump straight there, is that we can see that this starts at a magnitude of 1/4. So that matches that. It's a little harder to read over here, but you can certainly see that on the Nyquist diagram already. So as we increase omega, so that's going to slide this along, that these phi1 and phi2, so these are the only ones that are going to be changing. This phi4 and phi3 stay, and they essentially cancel each other out. And so then this is going to be a gradually increasing angle, phi1 and phi2. And so since that's increasing, the overall phase is going to be going more negative. And so that's this gradual curve to get more negative. And then when this S point at the omega value jumps over the value of 2, then we jump from phi4 being a minus 90 to phi4 being a plus 90. Otherwise, these vary continuously, and phi3 stays at plus 90. And so going from minus 90 to plus 90 is a whole sweep of 180 degrees. And it's 180 degrees in the negative direction because phi4 enters with this minus sign. And so that's what accounts for this 180 degree jump. And that 180 degree jump happens at exactly the value where omega is equal to 2, because this point right here is when omega is equal to 2. Simultaneously, what ends up happening is that the magnitude of the distance between the test point and this pole at s is equal to 2I is getting smaller and smaller. And so as we approach this point on the imaginary axis, M4 gets smaller and smaller, which makes this overall magnitude blow up because M4 is getting very, very small, so that makes this reciprocal value get very, very large. And so that accounts for this spike in the magnitude, and that spike in the magnitude happens again where omega is equal to 2. So that same point, we get this 180 degree jump, and we also get this spike in the magnitude. So that's our way of overall sketching the Bode diagrams. You could certainly continue to do this and indicate that these magnitudes are going to keep getting bigger and bigger as omega goes up and off of this towards the imaginary infinity direction. And so that's going to create these magnitudes that are just decreasing. Similarly, you could measure that as this again goes off to infinity, phi1 and phi2 will eventually go to both go to approximately 90 degrees. Phi4 and phi3 will all be 90 degrees. So the final asymptotic value here will be 360, which is 4 copies of 90 degrees. So when we take a look now at the Nyquist plot, which is our final goal, we're going to be able to again think through and observe the effect of these poles on the imaginary axis. So we can take a look at here. This is when s is equal to I times 0. So we're going to start essentially on the real axis when the test point is here, and as it moves, what's going to happen is, again, the phase is slowly decreasing, slowly going more and more negative. And so that's what's happening. It's going more and more negative along this direction. And then once it hits here, this is essentially at, I'll call it s is equal to 2I, and I'll just put a little minus on it, which means that, so it's going to be just before, I'll put that in parentheses, it means just before we hit the point 2I. Then it's going to take this jump all the way around, 180 degree jump, just like we're doing a 180 degree jump in the Bode plot. We're doing a 180 degree jump, that's an arc in infinity, to jump directly to this point, which corresponds to this new value here, the phase value that we get after the 180 degree jump. And then we continue moving along this trajectory until we go off to infinity. And again, we're entering this at an angle of minus 360, which is again entering essentially at 0. And so that's why the asymptotic direction that this is approaching is then at 0. And so keep in mind that the Nyquist plot, again, it shows you information about the negative imaginary axis as well. And so we have this flipped, and so that's why this gets a little bit complicated, but you can see that, that what we haven't highlighted already is the flipped copy of what we have highlighted. All right, so now the trick is to look at the Nyquist diagram and be able to determine stability. And so if we look at our transfer function, open loop transfer function, we have no unstable poles. So that means that if we have any encirclements, that means that we will have an unstable closed loop system. And so what's useful is to go ahead and find that point s is equal to -1. And so we could go ahead and put it here, s is equal to -1. And what we're going to observe, if we start here at the origin and we go ahead and trace this out, we're going to make half an encirclement, and then we're going to make one encirclement, and then we continue, and we're going to make another half encirclement and another one encirclement. So that's again 2 encirclements of the point -1 in the clockwise direction. And because that's non-zero, that means that this closed loop system is indeed unstable. And because, again, this arcs at infinity, make sure that this point is always included. That means that the number of encirclements isn't going to change, and so the system is always closed loop unstable. And so this is indicated by the fact that, again, you can see from the root locus that immediately these branches emerge in the right half plane, which means that the system will always be unstable. It's interesting to consider a very similar example, but one where the zeros actually appear as complex conjugates on the imaginary axis. And so that's what we have here. We have 2 poles at -1, and we have zeros at plus or minus square root of 3. And so that's what these 2 zeros are located here. And so we see a similar effect to what we saw before, but it's useful to, again, consider how all these different terms affect the Bode plot and then also the Nyquist. So remember that the transfer function, when we evaluate g of I omega, this is going to look like, if we call this 1, 2, 3, and 4, where 1 and 2 correspond to the zeros, then we're going to have m1, m2 over m3, m4, and it's going to be e to the I, and we're going to get psi1 plus psi2 minus phi3 minus phi4. And so the overall phase is going to be the sum where the zero angles appear with positive numbers and the pole angles appear with negative numbers. The magnitudes to the zeros appear in the numerator and the magnitudes of the poles appear in the denominator. So that difference affects how we sketch out the Bode plots because of the sign and whether the magnitudes appear in the numerator or denominator. So, so again, we can look at the angles. So again, the angles here. So this similar to the previous example, this angle, which is we call this psi2. This angle here is always going to be 90 degrees for the Bode plot, which is always positive, evaluated in the positive imaginary axis. So for psi1 is going to be negative 90 for the first bit until we reach this 0, and then it will be positive 90. Because that appears with a positive sign, that's going to exhibit itself as a positive jump of 180 degrees. And so that's going to happen when omega is equal to square root 3. And so that's exactly this value right here. This is omega is equal to square root of 3. And what we're observing here is that we get a jump of 180 degrees positive. And again, that's because these are zeros, they're adding phase. a jump of 180 degrees in the phase. Simultaneously, by the same explanation as before, the magnitude m1 is getting smaller and smaller as our point gets closer and closer to this 0 value. And then once it reaches that m1 value goes to 0. And because that m1 appears in the numerator, that essentially squelches this entire term so that the magnitude goes to 0. And so that's the reason why this magnitude goes off to 0. So this magnitude is getting smaller and smaller this direction. So that's why we get this spike in the downward direction at the same point omega is equal to square root of 3. So similar arguments could be made for evaluating the fact this starts at 0 and this ends at 0 and so on. And so I leave that to you to work out those details. When we look at the Nyquist plot, what we see is that this particular shape, again, because s is equal to -1 happens out here, that there's no factor of k that will expand this to include this. There are no open loop unstable poles, and so there are 0 encirclements at all values of k, so that means that this system is going to be always stable for all values of k greater than 0.